It is really a great pleasure to be able to give this talk here. And as Hao just said, I changed the topic because initially I thought I have to talk about something about boundary layer, and I think I really don't know much about boundary layer, and I feel very stressed. And later on I realized no one else is doing it, so I feel very relieved. Now I'm back to my favorite topic, which is icy satellites. Okay, so since both Daphne and Krista has already given a very nice introduction to icy satellites, so I'm not gonna bore you with all these, things about the general introduction, except saying that believe us, there are global ocean under the ice sheet. They are very cold. They are forming the outer solar system, but because of the tidal dissipation or some leftover heat or radiogenic heat production in the core, these systems still have a global subsurface ocean, and we know that for Europa because there's this strong magnetic induction signal found by the as it's generated, as it's surrounded around the spatially variant magnetic field of Jupiter. And for Enceladus, we know that there's a subsurface ocean, global subsurface ocean under the ice sheet for a slightly different reason. It's detected by the librational motion. Okay, so imagine that if the ice shell is frozen all the way in, and then you have a large moment of inertia of the whole, and the whole body have to move as a whole, then the librational amplitude will be much lower than what we observe. And also a fun fact about Enceladus, there's this over the south polar regions, there's this active geysers going on, and they inject and emanate these water vapor mixed with all kind of other materials into the space. And because the Cassini mission has this mass spectrometer, so they were able to detect some interesting, simple, organic matters in this plume. And there's also salt, silicon nanoparticles got detected, which seem to suggest that this material come from the deep ocean, not coming from the ice shell. And also it may link to the hydrothermal activities at the seafloor. Okay, so then the big puzzle here is really, why this system have so much energy in it? What keeps the ocean from freezing? If you notice, sorry, previous slide. Can I go? Okay. Enceladus has a radius of only 250 kilometer. It's really small. Okay, I'm not gonna say the same joke again. So it's really small, which means it's in the universe. It's just like a droplet. It will cool down almost immediately. Okay, over the geological time scale, it's gonna be like that frozen. But if it's not, which is really surprising. So where the energy comes from? Well, there's really no way that for Enceladus, for Europa, probably yes, it's larger. You have enough radiogenic materials there. But for Enceladus, really, there's no other reasons for it to have a global subsurface ocean. So the energy comes from its orbit. Okay, so Enceladus is in this elliptical orbit because Saturn is actually dissipative. Okay, and because of the Saturn's low quality factor, it exerts a momentum torque onto these icy satellites as they orbit around it and make their orbit eccentric. And then the eccentricity of the orbit is a kind of energy source. And that energy can be extracted and dissipated in the satellite system itself. Okay, so what happens there is that because the orbit is eccentric, so sometimes it's closer to the host planet, sometimes farther away. And that means the tidal force exerted on this body is time varying. So then the ice shell and the silicate core, the ocean, all the three layers together, they try to stretch. They will get stretched and compressed from time to time. And if you And of course, then dissipation can potentially happen in all three layers. We don't know where the energy dissipation exactly happens. And that's probably the largest uncertainty in the system. And it can happen in the ocean layer. you have this tidal bulge, and under the eccentric tidal force, the bulge is vibrating back and forth. So you're gonna have this elliptical instability. You're gonna trigger inertial waves and all that. So potentially they can, if you are lucky, you may even get into a resonant state. So you can generate dissipation in the ocean layer. But on top of that, you can also generate heat in the solid layers, which means the ice shell and the silicate core, right? And if you just imagine, right, if all the liquid and also the solid layers are more or less moving at the same speed or have the same amount of displacement, then you're probably going to generate more heat in the solid layers than in the liquid layers. But that is still, things to be studied because, liquid layer you may have resonance. But if you have this heat production generated in the solid layers, then you will get a heating profile that is polar amplified. And this feature has to do with how the eccentric tide works. Okay, so eccentric tide basically do two things. Imagine this is a planet, this is a satellite, right? It basically do two things. It stretch it like that, and then you do this, right? So all the polar regions really has the largest strain rate, and that's why naturally if you solve for the strain rate and you substitute if you substitute that to calculate into the formula to calculate dissipation, you find out that polar regions produce more heat.
That depends on whether you are dissipating in like thick spherical shell versus a thin spherical shell?
Yes, it varies. Yeah, if you do the tidal calculation for the ice shell for a solid body, it's gonna be different. And I'm glad you asked this question because also for Enceladus, another complication is we know the core is very porous. The mean density of the core is only 1,600 kilogram per meter cube, so it's like much lower than the density of normal rock. And if this core is porous, it really can do anything. The water can flow in, flow out. They can bring the hot water underneath outwards in a more concentrated way. So people have done calculation for that, but I don't think there's a conclusion about how the heating pattern should look like if you have, because it's a really complicated system. Imagine this is a porous viscoelastic material. So the dynamics, the dissipation in the liquid part, in the solid part, it becomes very complicated. Okay, so then, yeah, please.
How big is the displacement due to the tides on Enceladus?
Only.
They shall get moved.
Good question. I don't have the number on top of my head. In the order of 10 meters or something. Yeah. I want to use this diagram to just do a sketch about what is going on in this world. And I want to do this because I think most of the people sitting here may have some interest in this moon for this, because some of the dynamics you may be expert in that area. Okay, so I will try my best. So first of all, we have this heat generated. If there's heat generated in the silicate core, then the heat coming from the seafloor will become about this bottom heat flux from the core will drive convection, right? And we have our favorite rotating really Barnard convection. You have this thermal Rossby wave kind of pattern that rolls along in the low latitude, and we have these spiral things over the polar regions. And if the true Rossby number is low, right? So we have to understand we have to have some estimate for the true Rossby number. Okay, so how are we going to do that? One thing that we can do is to think about the energetics. So if we write down the energetics of this, by the way, this is work done by, this idea come from Malta Janssen. I'm very lucky to get involved in this work. So he said, okay, we should think about energetics because we have no clue about this system, except that energy got to be conserved, right? We have to have equal amount of energy coming in and going out. So if you write it down, there are all these contributions. And if we only consider the energy injection by convection, right? Then you can, and the dissipation by friction along the top and bottom layers, then you can write down this very simple energy balance. Right, on the left is the tidal dissipation. It's the frictional dissipation happening along the boundary layers. And on the right is the energy injection by convection, very simple. And then you can get, this really is the upper bound for the velocity that we can get in the system, right? And assuming that there's no other process that is dissipating. Usually you would have dissipation in the interior as well, but we ignore that, right? So we then estimate this velocity and calculate this true Rossby number using the result from this energy balance. Then we get here, we get this result, right? So for snowballers, which we don't care about, it's low. But for European insulates, we also get very low true Rossby number. These numbers, you can see 10 to the minus 4. So this is fast rotating system, and we are confident that if this estimate is correct, then we are probably okay to assume that we're gonna have this kind of dynamics. Yeah.
Where do you get your CD? Yeah.
Yeah, that's a large moving part.
It's a large what part?
Moving part. So there's a lot of uncertainty in that part. So we estimate this CD using the Earth's water ice CD, which is and we are being conservative and use a slightly lower number. It's 2 times 10 to the minus 3. And how large this CD is really depends on how rough the surface is. And since we don't have the roughness estimate and the estimate for the roughness, then we don't really know. But we base our estimate on the Earth's, water ice interface values. And luckily, this result is not extremely sensitive to CD because you have U to the power of 3 here. Yeah.
And you're claiming that these Rossby numbers are upper bounds?
Mm.
Okay, so maybe even smaller.
Yeah. Okay, so we have this, our favorite rotating convection happening in the system. I'm sure half of the people sitting in this room is happy now. And then what else? Okay, we have tidal response in the system as well. And we know that internal gravity wave, every time it bounces off a critical topography, it gets focused a little bit. And if you do that, if you are lucky, then you form a resonance chamber over the globe, and you will form these super thin shear zones in the system, and they propagate, and they can potentially resonate. Okay, and that can introduce additional dissipation in the ocean itself. Okay, and what else? Well, the ice shell is also librating. The librational amplitude is close to 100 meters along the equator. Okay, it's going back and forth pretty significantly. And there's a lot of topography in it. Well, then you can imagine that inertial modes will be excited because you push the system, you're creating vertical motions essentially in the system. And then also you're gonna have this elliptical instability. And near the water ice interface, you're also gonna form these shear boundary layers, probably also turbulent because the librational amplitude is pretty large. Then how the convection, the inertial waves is going to interact with this shear boundary layer, right? That becomes a question. And then comes my favorite part, which is the interaction between the ice and ocean. Okay. So in addition to all of this, we also know for Enceladus, because the tidal dissipation is polar amplified, we also have this ice shell that is power thinning, right? You have polar amplified heating. You generate a power thinning ice shell that's reasonable, yes. And this map is reconstructed using the surface topography, using the gravity data, the libration amplitude, all these things combined together. And Hemingway and Mita come up with this map. Right? And you can see along the equator is around 30 kilometers thick, the ice shell. And over the polar regions, on average, it's only 10 kilometer or so, and there's a very strong hemispheric asymmetry between the northern and the southern hemisphere. Okay, which is kind of mysterious.
And then what's the estimated depth? So there's delta of like 20 kilometers here.
Delta?
So the change in thickness is like 20 kilometers?
Yeah, 20 kilometers.
And then what's the depth of the ocean estimated?
40 kilometer on average. Yeah, so the total water ice layer is 60 kilometer. Okay. So then so when you have this ice thickness variation, what is going to happen is over time, under the pressure stress, the ice will basically just slowly flow, right, from the equator to the polar regions. And that flow mostly going to concentrate near the bottom of the ice because that's where the ice is warmer and less viscous. And we can actually estimate how fast this flow is. And then what this tells us is that you have to be able to form new ice at a rate that can compensate this ice flow. Otherwise, the ice topography cannot be maintained. Right? So this really tells us, when we observe this polar thinning ice shell pattern, it tells us that there must be new ice continuously forming near the equatorial regions and melting happening over the polar regions. And when that happens, you have this, you create salinity gradient between the equator and pole. Equatorial region where the freezing happens, you're going to have saltier water. Okay? And then on top of that, because we know the freezing point of water is a function of pressure, when you have this thick ice over the equatorial regions, the freezing point will be lower. Okay, so the interaction, by interacting with the ice shell, we naturally form meridional density gradient along the ice shell, where near the equator we have colder and saltier water than elsewhere. And we know from, by studying, if you look at Earth's atmosphere or Earth's ocean, when you have this meridional density gradient, what is going to happen next is baroclinic instability, right? So the cold fluid, of course, they're not going to stay there. What they want to do is they want to sink. They want to sink, and they want to fill the entire bottom ocean with the dense water, while as the buoyant water will remain near the surface. Right? So as a result of that, because when you do this kind of circulation, no matter what form it takes, may take form of eddies, the mean circulation, but no matter how you do it, this is the place where you have the coldest water. So any water that moves towards the equator is going to be warmer than it. That will lead to a converge of heat flux. Any dynamics in this system, because of this meridional temperature gradient, is going to converge heat towards the equator. And that's not good news for the equatorial ice shell, because with all the heat coming in, if this heat flux is really strong, it's going to melt the equatorial ice shell. So then, by observing this ice shell, we can put constraints on this heat flux, and in turn, on the dynamics that drives this heat flux. Okay, and as I just said, this cold water is going to sink. And then over the polar regions, we're going to form this stratification. Okay, now the system becomes slightly more complicated because when stratification kicks in, instead of inertial mode, we now have internal gravity mode in this area. And on top of that, what is it going to do to convection? Will the convection ignore stratification, just shoot upward? Probably not. It's going to stop. It's going to come to a stop. Convection cannot just, we're going to talk about it, but convection is certainly not going to ignore this stratification under the ice sheet. Okay, so then you may ask, okay, I said all of this. It sounds interesting. There are a lot of things going on, interesting, a lot of interesting academic exercise. So, but why is it useful, right? Eventually we need to come down to observables. So what are the observables? So from the mission, we can know we can get pretty good estimate about mean ice thickness variation, as we have already done for Enceladus. We can do the same for other icy satellites. And we can also measure how the ice shell move. Is there a long-term drift? If so, then probably that is caused by the drag from the ocean, right? If you have some current developing in the ocean, then the ice shelf can potentially drift. And then in the last week, we have this chemical composition, right? For Enceladus, we have these southern regions where you have active geysers. They send material from the interior to the space, so we can detect it and see what is in there, right? And chemistry, I don't understand chemistry, but people told me that if you know how it works, you can say a lot of things. You can tell how quickly things has been transported from other places to, because the chemical reactions happens all the time, and the fractionation they happens all the time. So if you know your work, which I don't, but that potentially can tell us something useful about the transport timescale, right? So okay, so for this audience, we have to convert this list of observables to something that we care more about, right? So first of all, the mean ice thickness tells us the total heat production rate in the system, because we have to be in the energy balance, right? The heat loss from the ice gel has to be in balance with the total energy production. So then the number one there can turn into the total heat production here, okay? And then the ice thickness variation can tell us how quickly the ice flow is acting, and also how large is the ocean heat transport. The ocean layer is the only liquid layer in the system. If you're relying on heat conduction in the ice sheet, in the core, it's not going to be very efficient. But because ocean is a liquid layer, it can redistribute heat really efficiently. And this heat redistribution can significantly change the ice thickness variation. And that ice thickness variation is something we can directly observe. Right? So then after we get estimate for ocean heat transport, we can then turn that into properties that controls the ocean heat transport. Yeah.
Yeah, can I just ask, for this ocean heat transport, you're relying basically on the ice flow, right?
The ocean heat transport, no, it's relying on all these dynamics I just reviewed.
Yeah, but then for the ice flow, which controls your melting and freezing rate,
Yes.
there's huge uncertainty in the basal ice viscosity.
Yeah.
Yes,
Okay.
which is like several hundreds of
Yeah.
magnitude.
Okay. Let me put it this way. So there are two balance we need to consider. One is mass balance. The other is energy balance. So in order for the ice sheet to stay there, we have to satisfy the mass balance. So coming from the mass balance, we can compute the freezing rate, melting rate here. But whether this freezing and melting rate can be sustained is a question, right? You have to be able to provide the right amount of heat flux to generate heat in the right places. Then you can sustain this freezing and melting rate. Then we have to write another equation for the energy balance. Right? Then, yeah.
Wait, but if I get Daphne's question, she's saying that's all set by the velocity on the ice flow.
Not
that's-
really. Okay, let me explain. So actually, if you do the number for Enceladus, the latent heat related energy is not the largest term in the system. And what else is going on is over the equatorial region, because your ice shell is thicker, so the conductive heat loss is slower than the polar regions. And the ocean heat transport is also really, so there are a lot of things going on. We have to consider all of them together. And then you will write down the equation for the entire the energy balance for the entire system, and making sure that energy balance is satisfied at each latitude, right? And because we observe this, so then we use the mass balance, we can estimate the freezing and melting rate, and then we substitute that freezing and melting rate into the energy balance equation. The energy balance equation tells us gives us constraint on ice flow and ocean heat transport.
Can I ask a related question?
Yeah.
For your freezing and melting, are they in steady state?
Assuming we assume in a steady state, that's how we compute it. Otherwise, we can't. If it's changing, then we got no information out of it. Yes.
So on Earth, we have this, on Earth's ocean, we have the same ingredients. So we have bottom heating, and we have salt production.
Yeah.
And at the end, the Earth's ocean is stably stratified.
Yeah, that's what I'm trying to say here.
But you also say that we had intense vertical convection.
Yeah, that's before I talked about the ice sheet. Yeah. Yeah.
So we are not sure it.
Yeah, then
it's just
we
a
have,
side
yeah,
of-
I hope we can get to the last part of my presentation, then I will talk about the
Okay, if I
stuff.
shut up, you can go to the end.
Let's make sure we get.
Okay, so then you have this, okay, thirdly, we have ice shell motion. It tells us ocean momentum transport. Then the ocean momentum transport, in order to deliver momentum from ocean to the ice sheet, you necessarily need to rely on either friction or form drag. And then if you rely on friction, then energy directly got dissipated. You rely on form drag, you trigger waves. The waves, sometimes they can turn back into mean flow, but sometimes usually they don't. They also break. So then that indicates a certain amount of energy dissipation in the system. If the momentum is successfully transported, they die one way or the other, right? And then we may use that to think about the thermal wind balance. So imagine that this system is stably stratified, and you have this meridional temperature gradient, then of course you're gonna have thermal wind. Then thermal wind can build a natural connection between what is going on, what is the isopignal looks like, and the shear in the ocean layer, in the ocean. Okay, and finally we have this chemical composition, and that will, as I just said, it will turn into some constraints on the ocean transport timescale. But we have to rely on colleagues in chemistry to do that conversion for us, because I don't know anything about it. Okay, so usually I would talk about mainly focus on the ice sheets, but this time I'm gonna switch a little bit. I'm gonna focus on the last one, which is the chemical composition. All right, so what is the motivation? Well, it comes from the polar region, the polar geysers on Enceladus. On Enceladus, if you take a picture over the South Polar region, you see this structure, 4 parallel linear, equally spaced stripes called tiger stripe, and out of it we see plumes made of mixture of water vapor and other materials injected outward. And one interesting constraint that people get from it is that they see nanoscale silicate nanoparticles. In Hugh et al., this is I think these papers attract really a lot of attention because they claim that because we observe these nanoscale silicate particles, then it means that this particle cannot stay in the water for that long period of time, otherwise it will grow very big. And then it puts constraints on the transport timescale. Okay, and of course, as you can tell from this argument, there are a lot of assumptions. So the ocean must be saturated. I don't know much chemistry, but the ocean must be saturated. So then the silicate nanoparticles will grow in size in time, right? So there are a lot of assumptions. But then I think from a fluid mechanics point of view, we can investigate whether it is possible to deliver something through ocean that is 50 kilometers deep over the polar regions within 2 weeks. I think that's something we can do. Okay, so then we wonder. So if imagine that there's some hydrothermal plumes, we make them as concentrated as possible, like super concentrated plumes. One single grid point in the simulation, right? And will this heat source being able to trigger some convecting plumes that shoot all the way to the ice sheet, right? That's number one question. It's important because if you write a proposal, then you have to say some biological activities in these hydrothermal vents. They're gonna create some biosignature that deliver it to the ice sheet, right? If they don't remain concentrated, then it becomes a problem. They got mixed, the super diluted, we can't really detect the signal. So that's an important question to figure out. Okay, secondly, we need to figure out how quickly this transport is. Right? A lot of the biomass, biosignatures, as far as I understand, they're time sensitive, so they decay over time. Then you don't want to spend too long in this journey. Otherwise, you will get nothing, right? So these are the 2 key questions we want to answer. And And finally, we want to get back to the question that Michael just asked. So if you have this ice thickness variation, can you really deliver anything across the stratified layer? Or to answer the question whether the ocean is going to be stratified or convective. Okay. We're going to start from the first one. Okay, point plume. So we start from a point plume, and this is an old topic that has been studied, in lab, in numerical simulations. And here I'm showing results from Goodman et al. 2012. What they find is that if you put a super concentrated heat source at the bottom of the ocean, initially you're gonna form this. Well, at the very beginning it's stable, but soon enough it becomes unstable and start to entrain, and then you form this cone-like structure. Cone-like structure here is kind of small in their simulation, and then at some point, because under the influence of rotation, the plume accelerate and the column got stretched, and you develop this circumplume rim current. And these rim currents inhibit the entrainment into the plume. So then the plume, the properties of the plume remain relatively stable for an extended period of time. And with this rim current, and you can see that in Goodman's simulation, you also see these vertical plumes. And this thing continues until the plume reaches the top. Okay, and this simulation, by the way, assumes a Europa setup. Okay, so then what happens is after it shoots and hit the top, then it undergoes baroclinic instability and scatters the heat away. But imagine, it's still, if this happens, we would claim that the plume is still concentrated, right? Because you still have this high concentration plume directly, from the bottom. Not significantly diluted, and on top of that, if you really have a heating, a lot of heat coming in a small area, then you may feel you may form a little cave under the ice sheet, which help you focus the heat even more.
And is this there's no stratification here?
No stratification. Yeah.
But in your model, the poles are stratified. So you have
not
to penetrate?
Yet. Not yet. Only the third part. Now it's all neutral.
Wanying?
Okay. Yeah.
You mentioned some particles and organic compound in the plume. This is not taking that into account?
Organic compound?
The diphasic nature of the plume. You have tiny particles and...
Yeah. It's just the motivation come from that work. They have this they find these nanoparticles from the plume, and then they say, okay, the transport timescale from the seafloor to the surface is very short, 2 weeks.
The particles are tiny.
They're tiny. They don't account for the existence of yeah. Okay. So then, since then 10 years later. A little bit longer than 10 years later, we now have better tools and we have more computers, so we can just do a little bit better simulation. So what we do here is we increase the resolution, and under the same setup is very similar. And what we see is that we see this development of these first two stages much better. You see this initial, laminar stage, and then it starts to become unstable. It fill up the cone, it fills up the cone, right, as we expected, and then it starts to get into this columnar regime where you have these cylindrical plumes going upward, and we are wonder. So when we run this experiment, we have this task in our mind that we want to understand what is going on in a super deep ocean. Right? So we make sure that domain is tall enough.
Is this DNS?
This is not DNS, LES. Yeah, DNS we can't study this problem in this scale.
And sorry, is L rot set by this rim current, or is it set by, is this some sort of inertial radius? What's setting L rot?
Okay, good question. So really in this system, if you think about it, there's only one length scale can be formed. if there, one length scale, If you don't imagine that, if there's no boundary effect, right? No boundary effect, no sidewall effect, no top, no H, no L, then really this system has this. What we need to provide to the system is this total buoyancy flux at this point, FB, and rotation rate. That's the only two, and out of that you can only form one length scale. So naturally, everything in this system should scale with this length scale.
And is that shown by the vertical dashed lines there?
Yes. I will get into the exact scalings later. Okay, so then, as I mentioned, we make sure that our domain is tall enough to make sure it's not directly impacting the top surface. So what happens there is that we find a third stage, right, where the plumes will undergo instability. Even there's no stratification, there's no top boundary, nothing happens. We just go unstable itself, and they scatter laterally. Okay. So now let's look into the details of each stage. I know you are puzzled, but we're gonna get to the third stage. We have to go through, stage by stage. First stage. Okay, so first stage is governed is not rotation governed. So there's this very famous model, Moulton-Taylor-Turner model in 1956. It's really simple, actually. Just take horizontal integration of your Navier-Stokes equation, assuming steady state. You're gonna get this. You have mass continuity. Basically says, okay, you have this mass flux coming in, and if you entrain material into the plume, then you will have more material to transport. And the second one, momentum. If you have mixed things, if you have buoyancy, then the momentum will be changed, and so on and so forth. Okay. So from this, we can actually solve this set of equation can be analytically solved, and you will get this MTT solution, which tells you that the shape of the cone should the radius of the cone should increase linearly with Z. Okay, and you can see it, and that this thing is plotted using the dash curve here, and you can see that it matches really well. And also from this, we can solve for the W profile and B profile. W is the vertical velocity, B is the buoyancy. And on the right, the solid curves are from the simulation, and dash curve are these solutions. And you can see they all matches reasonably well, except in this region where we can't really treat the source as a point source. It's not a geometric point. Yeah.
What determines the entrainment rate?
Usually people use this number. It's a fixed number.
And it matches well in the simulation?
Yes. This number initially is empirically determined, and it seemed to work pretty well. So, yeah. Yeah.
Can you replace your variable FB with viscous dissipation rate? They have the same dimension.
I'm sorry?
Can you replace FB with viscous dissipation rate?
Oh, good point. So, as I just, of course, if you consider viscosity and diffusivity, there's more than one length scale can be formed. But we assume that this system is turbulent enough. It's already in not strongly influenced by diffusivity and viscosity, so we didn't consider that. Okay, so then the stage number 2 is the cylindrical rotating plume stage. And on the right, we show this measurement by Fernando et al. In 1998 in his lab, and you can see that the radius of this plume, according to his observation, initially increases with time and then stabilizes. It doesn't change anymore after a while. And this transition, so he's done a lot of experiments, and this transition happens at a height of HC and the radius of RC. And these both things correlate well with the scaling. And again, because the system, if you only consider B and F, there's only one velocity scale, one length scale that can be formed. So that's naturally the choice. Okay, and we compare our result with the scaling. They seem to match reasonably well. The black dashed line here is the scaling. Okay, so now we come to the third stage. So I think probably I'm not going to convince anyone if I don't show an animation to let people know how the system developed. So initially, at the very beginning, you have this plume, but you can see soon enough, the plume just stopped growing. And on the right, we calculate the highest point of the plume.
What are you plotting?
So there are two measures. One is we define an envelope and we find the highest point. The other is we just track the center height.
But on the left.
On the left, yes.
What's being plotted there?
Oh, what is plotted is called the relative concentration. So we release tracer at the bottom to track how the material moves. So as you can see, over time, it just spread horizontally. It doesn't grow vertically anymore, and it doesn't touch the top surface. So this process, we think it can be described as following. So what happens is that this plume at some stage just become baroclinically unstable, and start to scatter laterally. And when the lateral heat flux, U prime B prime 2 pi r dz, when that heat flux equals to the heat supply from the bottom, which is F naught, then all of the heat is leaked to the side, and the plume cannot grow anymore. So then we substitute some scaling for U using the rim current velocity, using the thermal wind, and B using the scaling from the Fernando scaling. Then we can calculate. Then we can calculate. We find out that this final height HF should also scale with L route, which is a very boring result because really there's only one length scale in the system. So then we want to confirm that, so we run experiments with different L route.
Are you sure your power is 1/4 and not 1/2?
It's 1/4. That is because this FB is the integrated heat flux. Integrated heat flux in the unit of watts, not watts per meter square. Yeah. So you can see we run experiment with different L route. Initially the plume grows and then they all plateau at some point, and then we collect at what height they stop growing, and we plot it here on the right, which is the HF, plotted as function of our scaling L route. And you can see that they fall into a very nice line, and I think I'm in a big trouble now, so I have to accelerate a little bit. Okay, so we form this correlation, which indicate that this scaling works. Okay, so then because we know.
Can I just ask one question going back? Sorry, I know you're.
Yeah.
I'll ask later. Later.
Because we know how the system evolved. Initially it's a column and then spread. We know the sizes for all these things. Then we can finally get back to answer the question. Okay, is this plume gonna reach the surface undiluted, diluted? Is it gonna hit the side walls? What is gonna happen, right? So, of course, and we divide the entire system. There are two non-dimensional numbers in the system, formed out of 3 length scales. Besides L route, we also have the domain height H and the domain width L. Right? Out of that, you have 2 non-dimensional numbers, and we can divide the system into 4 parts. I'm not gonna. It's basically just the simple geometry, right? Is the box gonna fit the plume in at what stage, right? It's purely just a very simple primary school geometry. So then we have these 4 regimes. As you can see, in this laterally constrained regime, the plume is gonna fill up the entire horizontal plane, and it's gonna basically proceed as a uniform heat flux. It doesn't really matter what kind of heat flux you prescribe at the bottom; it's all uniform. Okay, and then in this stage, the plume is going to hit the upper surface as a non-rotating plume. So you see this cone-like shape all the way through the domain. Okay, and in this regime, you also have a focused plume hitting the upper surface, but it is in the rotating regime. So you have this, comparing this result to this result, you see the shape, their shape is slightly different. Okay, and finally here, as we said, at some point the plume will become unstable. It will stop growing, no matter what. So if your domain height is higher than HF, which is the final plume height, then anything will be homogenized horizontally, and that's what we see in this simulation. Okay, okay. So where are Enceladus, Europa, and Earth, right? So we have this estimate. We assume that the heat flux is probably not going to be greater than 10 gigawatts per plume. So then we have this regime set up here. And for Enceladus specifically, it is in this horizontal, is unstable plume in this regime, which means no matter what heating pattern you prescribe at the bottom, if it's like in a small scale, it doesn't really matter. It's all get horizontally homogenized. Okay, and I think I'm gonna skip this basically saying that we also did the same work for line plume, because some people say there's the plume is focused line, not point. But you can do similar stuff, and you get this regime diagram. Okay, so now let's get to the second topic, which is the transport timescale. The transport timescale. The key. So then we want to ask. So what is the key non-dimensional numbers in the system? And there have been a lot of discussions about whether diffusive free scaling eventually will emerge in the system. But I just want to say that actually from Earth oceanography point of view, usually the non-dimensional numbers that we use the most are usually not related to diffusivity or viscosity, mostly because Earth is a very there are a lot of things going in the boundary layer. You don't have a perfect boundary. Okay, and this motivates us to use the modified flux Rayleigh number instead of the Rayleigh number Ekman number combination. And it basically the reason why we want to use the flux Rayleigh number is because before running the simulation, we don't really know delta T. That's a problem, right? If you set your model up, you want to answer some question, but if you don't really know what number to put in, it's a problem, right? So then that's why we switch to flux Rayleigh number, and then the flux Rayleigh number, if usually the traditional flux Rayleigh number is combined with Ekman number, usually the flux Rayleigh number is a huge number and Ekman number is a tiny number. So assuming that the system is turbulent enough, diffusivity doesn't play too much of a role, then I think probably it's quite informative to just use the modified flux Rayleigh number where all the nu and kappa are cancelled. And this is in the formula, the definition of these numbers given here. And I just want to point out that this modified flux Rayleigh number is actually a very commonly used non-dimensional number in oceanography, which is called natural Rossby number. This natural Rossby number simply is just square root of modified flux Rayleigh number. And the physical meaning of that is basically how many rotation rate it takes for something to transport it from the bottom to the surface. And just want to try to build some connection here. Okay, so then regarding the transport timescale, historically there has been a lot of scalings around, and one of the scaling is the free fall scaling. And free fall scaling is quite intuitive. You just calculate how much, if you know delta T, then you calculate how much acceleration rate is using alpha G delta T, and then you can then estimate, okay, over a distance of h, how fast your velocity is going to be. It's going to be this much, and then you can compute your transport timescale. However, there's a very strong assumption built behind this argument, and that is all the potential energy released in the system converts into kinetic energy, convert into well-organized kinetic energy in the efficiency of 100%. Right? Then you get into this free-fall scaling. And you have this, and then, of course, as I said before, we don't know delta T. So we can estimate delta T using this Nusselt radian number scaling to calculate delta T. And finally, we get this free-fall scaling written in the modified flux radian number. Oh, really? Apparently, I don't have time to talk about stratification at all. But I will try to wrap this part up. Okay. So then the CIA, there's another scaling, CIA scaling, which is inspired by Arnold, Julian et al. 2020. So I think I don't need to talk too much about the details. Basically, just write down the balance between CIA and you solve it. And you will realize that this U over U FF, the characteristic velocity scales with free-fall scaling times this factor. And then we got a different advection timescale, which is to the power of modified flux radian number to the power of -2/5, not 1/5, okay? And then there's this long-existing scaling by Fernando when he did his initial lab experiment in 1991. The argument is pretty simple. It's just that there's only one velocity scale can be formed out of the system. And that's the velocity. And you just divide the h over that velocity, you get another length scale. And that transport time scale scales with really modified factor to the power of -1/2. Okay. And he showed that in his lab, his results agrees with this scaling. And finally, there's this scaling based on Nusselt number. So just think about this problem. If you want to understand how quickly some tracer is transported from bottom to the surface, and the tracer is exactly correlated with temperature, then there's really no difference between transport heat versus transport tracer, right? They're the same set of equations. So then we can directly estimate the transport timescale directly based on some Nusselt number estimate, and that can be done here. So this is really just pure definition, and then we can out of that we can solve for the characteristic vertical velocity, and again the transport timescale here, and then if we substitute the diffusive Frey scaling of Nusselt number, and then we substitute the definition of our natural Rossby number or modified flux radian number, we get a slightly different scaling. Okay, I know that you are all very confused, so I summarize all the scalings here. So there are 4 scalings I just discussed. The free-fall scaling, if you substitute in Solis parameter, which has a natural Rossby number of 10 to the -6, then you will get these numbers, right? CIA scaling, Fernando scaling, and Nusselt number scaling. And they are quite different. The question is which one is the most relevant, right? So we want to verify that somehow using either numerical simulations or lab experiments. So I don't know how to do lab experiments, so we just steal data from Fernando et al. So then, and these are the, I believe these are the red crosses. And we also do some simulation. We have near global simulation with strap heating, with uniform heating, local domain, large domain, anything. So we throw all the simulations that we have done in the past, global, anything, into this diagram. And they all seem to align very well more or less along the same slope. What happened? Okay, they more or less align the same slope. And then we also take, because we want to make some comparison, we also take the data from Gastin, and but the definition of the transport timescale taken from Gastin and all is slightly different from ours. We release Lagrangian tracers in our experiments. But in Gaston, I believe what we did is we basically take the Nusselt number. So we do expect that Nusselt number scaling to completely agree with the red dot, yellow dot here, because they come from the same source. But anyway, so when we put all these things together in this diagram, my impression is that it's very difficult to tell these three apart. It really can be anything. So probably, but what is certainly, but what we are sure about is that probably it's not the free fall scaling. Yeah. So then our conclusion is the transport timescale on Interplay is at least in the just some simulations, and at least hundreds of years and plus. Okay, and I don't have time to talk about stratification, but we can talk about it afterwards.
All right, thank you.